Section 7.5, Fugacity and the equilibrium constant for real gases. For an ideal gas, the chemical potential is equal to mu naught plus RT times the logarithm of P over P naught. For a real gas, we simply replace this P with F, fugacity. What is fugacity? Fugacity can be viewed as the effective pressure of the gas. Fugacity takes the attraction and repulsion between gas atoms or molecules into account. When P approaches zero, the pressure is low, then the fugacity approaches pressure. Because when pressure approaches zero, usually we have a very large molar volume, the distance between molecules is very large, and therefore the attraction and repulsion become negligible. Fugacity is related to pressure. Fugacity is equal to the fugacity coefficient times pressure. Over here, this fugacity coefficient gamma is equal to 1 for ideal gases, or even for real gases, as long as the pressure is low enough, this gamma approaches 1. So here is the equation to compute gamma. I'm not going to prove this. The logarithm of gamma is equal to this integral from 0 to pressure P. What integral? Z minus 1 over P prime times dP prime. P prime is a dummy variable. You can replace this P prime with any other variables. The reason I use P prime is because I used P for the upper limit. So we can actually measure this Z and plug it in and then integrate this Z over Z minus 1 over P prime, and then we can get the logarithm of gamma, the fugacity coefficient. And also you can see from this equation, if Z equals 1, what happens? When Z equals 1, this integral is 0, then gamma is 1. Well, if Z is 1, gamma is 1. That's for ideal gases. What if the attraction is predominant and then Z is less than 1? When Z is less than 1, we're integrating a negative function. Then this logarithm of gamma is negative. Gamma is less than 1. What if Z is greater than 1? That happens when the repulsion is predominant. When Z is greater than 1, this integral is positive. The logarithm of gamma is positive, then gamma is greater than 1. So again, this gamma and Z are greater than 1 when repulsion is predominant. Gamma and Z are both less than 1 when the attraction is predominant. And also when gamma is less than 1, we know fugacity is less than pressure. When gamma is greater than 1, the fugacity is greater than pressure. For a van der Waals gas, when the attraction dominates, usually B is negligible. And then we can rewrite this van der Waals equation. P is roughly RT over Vm minus A Vm squared. So here we're assuming the attraction is predominant. And then we can compute this Z. Z is P times V molar volume over RT. So we plug in this as the pressure here, and we get 1 minus A over VMRT. So we just proved that when the attraction is predominant, Z is less than 1. And when Z is less than 1, again, this is negative. Therefore, this Ln gamma is negative. Gamma is less than 1. Now let's look at the other case. When the repulsion is predominant, A is negligible. And this van der Waals equation is approximately RT over Vm minus B. And then clearly we can prove this Z is Vm over Vm minus B. This is greater than 1. So Z is greater than 1, and also gamma is greater than 1 because this integral is positive. Now let's get back to the chemical reactions. For a general chemical reaction like this, we can write out the equilibrium constant of pressures, assuming all gases are ideal gases. It's very simple. We put the products on top, reactants on the bottom. Whenever we see a pressure of a gas, we divide that pressure by P naught. This is to compare the pressure with the standard pressure. And then we take care of the coefficients. Finally, we put this EQ in the subscript to emphasize this is the equilibrium partial pressures for X, Y, and B. And then we have this equation. The standard Gibbs energy of the reaction is equal to negative RT Ln Kp. Again, these equations are for ideal gases. What if we are dealing with real gases? We need to modify the equilibrium constant. Now we have equilibrium constant of fugacities. When we are talking about fugacities, we simply replace every P with F, the fugacity. That's it. And then we can tell that this Kf is proportional to Kp. But Kf is Kp times something else. Over here, we have the fugacity coefficients of X, Y, and B. They all play a role here. And then in this case, when the chemical reaction involves real gases, the more accurate equation is this. The standard Gibbs energy of reaction is negative RT times the logarithm of the equilibrium constant of fugacities instead of pressures. Again, in the end, the fugacity is the effective pressure of the gas that takes the attraction and repulsion into account in the equation for chemical potential.